We will continue with Module 9 on flexible pavement rehabilitation. We just went through the Pavement ME design software under Part B of Module 9. This part basically illustrated and demonstrated the software and some of the inputs required for flexible pavement rehabilitation. This section of Module 9 is considered Part C and will explain the models and transfer functions that are specific to flexible pavement rehabilitation, as well as the different rehabilitation input levels for flexible pavements. Part C is grouped into 3 topics within this session. They are the distresses in existing asphalt pavements, reflection cracking of existing cracks or joints through the asphalt overlay, and smoothness degradation of asphalt, jointed plain concrete pavement, or continuously reinforced concrete pavement overlays of flexible pavements. This specific part of distresses in existing asphalt pavement will also review 3 distresses. The first, and how they are considered in the Pavement ME design software and how they might differ from new flexible pavement design. First is rutting, then bottom-up fatigue cracking, and then transverse cracking. So the rut depth transfer functions to calculate the rutting in the asphalt overlay and existing asphalt layers, as well as the unbound layers and subgrade layers, are the same as related to new flexible pavements. In other words, there is no difference in the transfer functions or models between new flexible pavement design as well as flexible pavement rehabilitation design. The critical response is vertical elastic strains in the sublayers of the asphalt overlay and existing asphalt layers, as well as in the existing unbound layers and subgrade. Module 6-1-1 provided an explanation of the models, the mechanisms, and transfer functions for rutting measured at the surface. That methodology is applied also to the rutting in the existing pavement as well as in the asphalt overlay for flexible pavement rehabilitation. The existing pavement layers already include damage, the existing asphalt surface, and any intermediate layer and existing asphalt base. They already include damage related to rutting, while the new asphalt overlay does not. So how is the existing rut depth damage considered in the Pavement ME software for rehabilitation design? Or what is time zero in predicting continued rutting in the existing asphalt as well as the existing unbound layers and subgrade versus the asphalt overlay? The same methodology of strain hardening is applied to the existing asphalt and unbound layers and subgrade layers. The rut depth transfer functions to calculate the rutting in the asphalt overlay and existing asphalt layers, again, are the same as displayed on the graph in the slide. And the difference between the predicted rut depths for new and rehabilitated flexible pavements is the strain hardening concept used for the existing pavement layers. In actuality, the strain hardening concept is also applied to any new asphalt layer and unbound layer for the different rut depth increments for different load levels or truck types, truck loads or axle loads, as well as for the different seasons. So the strain hardening concept is used both for new flexible pavement design and predicting rut depths, as well as for rehabilitation flexible pavement design of flexible pavements. So we're going to basically review how that strain hardening approach is applied. So entering a rut depth for a layer for flexible pavements, because in the Pavement ME design software, as we illustrated in part B, where we showed the software, a rut depth is entered for basically each layer. The plastic strain associated with that rut depth, either in the asphalt layer or unbound layer, is set as 0 and is the starting point after overlay for additional accumulations of rut depth. So specifically for the asphalt layers, we have an existing rut depth that is related to or defined by an axial plastic strain. So the strain level then corresponds to a specific point on the transfer function between number of loads and axial plastic strain. That becomes the starting point for accumulating additional rut depths in the existing asphalt layers. So the rut depth in this example at this point becomes 0. And then as additional axle loads or truck loads are applied in different seasons, then the rut depths within those asphalt layers continue to accumulate. However, it is at a much reduced rate as compared to the initial part of the rut depth accumulation relationship. For the new asphalt layer, the starting point is basically N equals 1, or with the first truckload application. And then the rut depths or the axial plastic strain then accumulates from that point throughout the overlay design life of the rehabilitated flexible pavement. So if we entered 0 rut depth for all layers, including the existing layer, this is where the plastic strain is set or would start and is set to 0. And then it would start to accumulate after overlay. And as you can see, we would well over-predict the amount of rutting in the existing asphalt layers. Using the strain hardening concept, the amount of rutting in the existing asphalt layers, as well as in the existing unbound layers, the additional accumulation of rutting is much less because of the strain hardening approach, because it is accumulating, or the rut depths are accumulating at a much slower rate. So fatigue cracking in terms of asphalt overlay design for flexible pavement rehabilitation. Bottom-up fatigue cracking, basically the transfer functions to calculate the bottom-up fatigue cracking in the asphalt overlay and existing asphalt pavement layers are the same. The transfer function is shown on the slide, and that transfer function is used both for the asphalt overlay as well as the existing asphalt layers, because it has existing damage. The existing asphalt layers already have damage, while the asphalt overlay does not. So again, how is the existing fatigue damage in the existing asphalt layer considered in the Pavement ME design software for rehabilitation design? Also, the key or critical pavement response is the elastic tensile strain at the bottom of the asphalt, the new asphalt overlay, and the bottom of the existing asphalt layers. So it's still the tensile strain at the bottom of the overlay and tensile strain at the bottom of the lower asphalt layer that's used to define damage in the existing asphalt layers and asphalt overlay. And then once the damage is defined, then the amount of bottom-up fatigue cracking can be calculated using the transfer function. So, predicting continued fatigue damage and cracking in the existing asphalt layer. How is the fatigue damage accumulation in the existing layers, the fatigue damage in the existing layers, how is that accounted for in the asphalt overlay design? Because we can have, there is cracking that can occur or has occurred in the existing asphalt base that are propagated to the surface, but not all cracks may have propagated to the surface from bottom-up fatigue cracking. So the difference between the predicted fatigue cracking for new and rehabilitated flexible pavements is the damage accumulates from the damage associated with the cracking amount in the existing layers. In other words, fatigue cracking transfer function to calculate the fatigue damage in the asphalt overlay and existing layers are the same. The critical response again is tensile strain, which is associated with the damage index in the lower layer of the existing asphalt layers, which are used to determine the starting fatigue damage index after overlay placement, as illustrated in the graph and slide. So entering the amount of bottom-up fatigue cracking defines the damage index and the starting point as times 0 for the existing pavement layer after overlay placement. So if we have, let's say, 9% total lane area of bottom-up fatigue cracking in an existing layer, that then defines the damage index in our calibration curve to start for additional accumulation of damage index in that existing asphalt layer. And then the damage continues to accumulate after overlay placement in terms of the calibration relationship. So for the new asphalt layer, the damage index is 0, so the starting point is no fatigue damage index, and so no cracking. So the amount of cracking then defines that is observed on the surface, then that defines basically the damage index, the fatigue damage index that's used in the transfer function. And then as additional truckloads are applied to the flexible pavement, then that damage continues to accumulate relative to the calibration relationship. And then additional fatigue cracks, bottom-up fatigue cracks, are predicted for the existing asphalt layers. Transverse cracking in terms of asphalt overlay design. The critical response is the tensile stress at the surface, and the incremental increase in the stress intensity factors in the asphalt overlay. So the transfer function is the same for new asphalt pavement design relative to flexible pavement rehabilitation and the asphalt overlay. The elastic tensile stress and stress intensity factor at the tip of the crack in the overlay are the key or critical pavement responses. So for the existing asphalt layer, since it's no longer a surface layer, no additional transverse cracks or thermal-related cracks are predicted for this layer. Only the wearing surface applies to the thermal transverse cracking of both new flexible pavements as well as rehabilitated flexible pavements regarding the asphalt overlay. So new transverse thermal cracks are only predicted for the asphalt overlay. The transverse cracks in the existing asphalt layer are used to predict transverse reflection cracks through the asphalt layer. So for the new overlay, only new transverse thermal cracks apply to this layer. The transverse cracks in the existing asphalt layers then are used to predict the reflection of those cracks through the asphalt overlay. Now let's turn our attention to the reflection cracking of the existing cracks or joints through the asphalt overlay. So this will be the next session within Part C of Module 9. The information presented and explained in this session is the same as discussed in Module 6-2 on semi-rigid pavements related to the reflection of transverse shrinkage cracks and fatigue cracks in the chemically stabilized base layer through the asphalt layers. In addition, Module 8 also included the same information on reflection cracking of asphalt overlays of jointed plain concrete pavements, fractured jointed plain concrete pavements, and continuously reinforced concrete pavements. So this will be a quick review under Module 9 for reflection cracks because the same models and mechanisms apply in terms of reflection cracks apply to all of the previous as well as this module itself. So the software considers fatigue and transverse cracks separately for all design stages, both new design as well as rehabilitation design. The reflection cracking methodology is based on fracture mechanics. Again, this is also the same as for reflection cracking of asphalt overlays of jointed plain concrete pavements, fractured jointed plain concrete pavements, and continuously reinforced concrete pavements that were discussed under Module 8. This information is included in Module 9 for completeness. So the methodology and concepts were previously presented and discussed in Module 6-2, so the following is just a summary as included in Module 6-2, as well as in Module 8, related to the reflection crack prediction for semi-rigid pavements, as well as asphalt overlays of concrete pavements, is the same for flexible pavement rehabilitation. So this just shows the fracture mechanics approach. It's divided into two parts. A similar approach is used for both transverse and top-down fatigue cracks that were previously discussed in Module 6. So it's composed of two parts: the incremental change in crack depth as a function to increases in the number of load applications as related to the incremental change in the stress intensity factor. Remember, A and N are the fracture parameters from the forum fracture mechanics or the Paris law. The second portion is the change in crack depth or increase in crack depth caused by incremental changes or increases in thermal cycles related to the stress intensity factors related to thermal cycling rather than through the number of load cycles. The A and the N fracture parameters are illustrated here for completeness, but have already been discussed in Module 8 on asphalt overlays of concrete pavements, as well as the asphalt layers over a chemically stabilized subgrade in Module 6-2. Again, reflection cracking mechanism is composed of three parts. There is a shear part that basically controls a thermal part and then a bending part. The shear part is the differential vertical deflection across a joint and or a crack as the wheel load moves across that joint or crack. The thermal is thermal cycling that increases the tensile stress above that joint or crack, and bending component, or the bending component, is the increase in flexural bending when the wheel load is located directly over the joint and or crack in the existing pavement, regardless of whether it is a chemically stabilized layer, a concrete pavement, and or a flexible or asphalt pavement. This illustrates the reflection cracking mechanism in terms of the differential movement from bending, shear, and tension, which is related to the increase in stress intensity factors for each. And again, the total change or increase in crack depth is basically defined by the increases in the number of wheel loads as well as the increasing number of thermal cycles. These two are initially kept separated because one is from a thermal event and the other is from a traffic load event. The damage then, or the increase in the stress intensity factors, are then converted to an increase in the damage index for a specific interval being some time event or time-related event through a season, month, or whatever that interval is, including traffic as well as the thermal event. So the change in the stress intensity factors are converted to a change in the damage index. And then just like for fatigue cracking, the total damage index is defined by the accumulation of the damage index in terms of reflection cracking throughout the design period. And then this is the reflection cracking rate transfer function that's used to predict reflection cracks in the asphalt overlay. And then this is simply a summary of the calibration factors of the transfer functions. The damage index stress intensity factors, the K1, K2, K3, 1, K2, K3, their values, and then the damage index calibration coefficient for the stress intensity factors, C1, C2, C3, C1, C2, C3, and then the transfer function calibration coefficients for the cracking model. And that's C4 and C5, C4 and C5, which is defined by the damage index. So it's been previously discussed, so that's for completeness. That's a basic overview of the same information that has already been discussed in Module 6-2 and Module 8. So the next session, or moving on to the prediction of smoothness, or IRI, of asphalt, jointed plain concrete pavement, and continuously reinforced concrete pavement overlays of flexible pavements. The roughness regression equation to calculate IRI throughout the design period of asphalt overlays of flexible pavements is the same as for new flexible pavements, which was covered in Module 6-1-4. This shows the regression equation as well as the regression equation for the site factor. So the site factor regression equation is the same, and the IRI regression equation for predicting IRI throughout the design life is the same as for new flexible pavements, which have already been discussed in Module 6-1-4. The roughness regression equations to calculate IRI throughout the design period for concrete overlays of flexible pavements are the same as for new jointed plain concrete pavements with an asphalt base, which was covered in Module 5-1-3, and is also the same for the new CRCP with an asphalt base pavement as was covered in Module 5-2-2. So the regression equation, JPCP overlays of flexible pavements, is the same as for new jointed plain concrete pavements. And then the regression equations to predict IRI over time for CRCP overlays of flexible pavements is the same as for new CRCP designs. The site factor for both JPCP and CRCP overlays of flexible pavements is the same, which is also the same for new jointed plain and or continuously reinforced concrete pavements, which is shown on the slide. Reliability, as we've noted in previous modules, was discussed in detail in Module 3 and how it is applied in the Pavement ME design software. The standard deviations of the residuals for the asphalt, JPCP, and CRCP overlays of flexible pavement smoothness is displayed on this slide. The standard deviation of the residuals is used to determine the reliability as related to smoothness of overlays of flexible pavements. Now that we've finished the continuation of the different distresses, the models and transfer functions that are included for rehabilitation of flexible pavements, now we're going to move on to the rehabilitation design input levels, at least discussing the different rehabilitation design input levels for flexible pavements. So this is still a continuation of Part C of Module 9. So there are 3 rehabilitation design input levels. Level 1, rehab design input level 1, is using non-destructive deflection testing and back calculating the elastic layer moduli, which are entered directly into the Pavement ME design software. That's not to say that the surface condition and distress surveys are not used for rehabilitation input level 1, because they are. But the damage of the existing pavement is based on the non-destructive testing and back calculation of layer moduli. For rehab input level 2, the damage of the existing surface or the existing asphalt pavement is based on the surface condition or distress survey and its assessment. And then finally, rehab input level 3 is based on a subjective rating or surface condition. And we're going to briefly go through each of the rehab input or rehab design input levels. So starting with rehabilitation design input level 1, FW testing and back calculation are used. The FWD testing along the wheel path of the project, including cracked areas, is used to determine or measure the deflection basins, which are then used to back calculate the mean layer elastic modulus for each layer along the project. For the asphalt layers, the asphalt temperature at the mean depth of the asphalt layer is also recorded during testing, or it can be calculated external to the Pavement ME design program. And so the elastic asphalt modulus determines the in-place damage of the existing asphalt pavement. So we're measuring the deflection basins in the wheel path along the project. We're then using the deflection basins that were previously discussed in Module 7 as an overview of pavement rehabilitation. We're using that data to then back calculate the modulus of the existing asphalt layer or layers, and then the resilient modulus of any underlying aggregate base layer and different subgrade soil strata. And that is used to determine the in-place damage of our flexible pavement. So the visual distress data is still needed and required for rehabilitation regarding input level 1. Basically, the length of transverse cracks are used for reflection crack prediction of transverse cracks. The total depth is measured of rut depth. The total rut depth is measured at the surface for predicting rut depths, again, using the strain hardening concept that we previously discussed. And then other design features and materials related to stresses are used, such as debonding between layers, stripping, raveling at the surface, whatever surface distresses are observed and recorded at the surface of the asphalt pavement. So they're all used in establishing a rehabilitation design strategy. So how is the damage accounted for, the fatigue damage, bottom-up fatigue damage accounted for or determined in rehab design input level 1 from the back calculated elastic layer moduli? So this is the regression equation for determining, or the equation used for determining, the dynamic modulus master curve as shown by the blue, as also the dashed red line in the graph. This is the dynamic modulus master curve. The blue curve represents, or what is termed as, the undamaged relationship. And this would be the relationship that is measured in the laboratory where you have no fatigue damage in those asphalt or laboratory prepared test specimens, or even from cores. The dashed red line represents the back calculated damaged dynamic modulus master curve. And so basically the difference is between the undamaged and damaged, either at one reduced time and dynamic modulus from back calculation, or multiple points. That average difference between the undamaged and damaged relationships defines the in-place damage of the asphalt pavement. So that's basically how the fatigue damage is determined, and then the fatigue damage is used to define the amount of cracking, bottom-up fatigue cracking, in the existing asphalt layer. This now shows an example that if we had an existing fatigue damage of 5% total percent lane area, you can see that there's almost no difference between the undamaged laboratory measured master curve and the back calculated elastic modulus of the existing asphalt layer from deflection test. They're almost equal, so there's very little damage in the existing asphalt layer. As we start to increase the amount of cracking and or damage, this shows the relationship. Now the blue line is still the undamaged relationship measured in the laboratory. The dashed curve represents the damaged master curve and is defined from the back calculated elastic layer moduli of the asphalt layers. And then the final graph shows the existing fatigue damage at 50%. And then you can start to see that there is a greater difference between the undamaged relationship and damaged relationship. But you can see that there's not that much of a difference between the undamaged modulus and the damaged modulus that corresponds to 50% bottom-up fatigue cracking, which would be considered a lot of fatigue cracking in an existing asphalt pavement. So going back and looking at the previous example, a much bigger difference between the undamaged and damaged, and then these graphs that doesn't take much of a difference in terms of the back calculated elastic layer moduli of the asphalt layers to relate to a lot of bottom-up fatigue damage in that asphalt layer. So in conclusion, the changes or differences between the undamaged dynamic modulus or laboratory measured values and the damaged elastic modulus or back calculated elastic modulus from deflection basins has a significant impact on fatigue damage of the existing asphalt layers. And so if a user is using input level 1 and sees that there is a big difference between the damaged and undamaged layer moduli, then the program is going to calculate or determine that there are a lot of bottom-up fatigue cracking in the existing asphalt layer. Now moving on to using or back calculating the layer moduli for unbound layers. In other words, FWD testing and back calculation of elastic layer moduli for defining the in-place elastic modulus of the unbound layers. Two important items. The moduli are determined at the in-place volumetric and physical condition of the unbound layers. The laboratory resilient modulus testing or default values included in the Pavement ME software are determined or represent the condition at optimum volumetric properties of the materials. So the question is, do the in-place moduli from back calculation of the unbound layers equal the laboratory measured modulus at the same water content and dry density? And this was also discussed in Module 4, Module 4-1 and or 4-2 and 4-3 on the use of modulus and volumetric properties for unbound layers. So we start with the elastic modulus, back calculated from FWD, which represents the in-place water content and dry density. We're then going to apply the AASHTO C factor in terms of adjusting the back calculated elastic modulus of the unbound layers to represent the laboratory derived values. So we adjust the in-place water content to optimum water content, and then that is used to represent the resilient modulus that has been measured at the optimum water content and maximum dry unit weight in the laboratory for the global default values relating resilient modulus and the volumetric properties under controlled testing conditions. This just shows the table in this slide is table 10-8 in the MEPDG Manual of Practice. The C factors, basic as shown here, basically convert the elastic modulus of the subgrade and or base to a laboratory measured modulus at the in situ moisture content and dry density using the AASHTO C factors. So if we have a flexible pavement, we have an aggregate base that's placed below an asphalt layer, then we multiply that back calculated modulus for the aggregate base by 0.62 to get the resilient modulus representing a laboratory equivalent value measured at the in-place water content and dry density for entering in the Pavement ME software. If we have a subgrade value below an aggregate base material for a standard traditional flexible pavement, then that back calculated resilient or elastic modulus of the subgrade is then multiplied by the C value of 0.35 to obtain the resilient modulus that's entered into the Pavement ME design software. So the C factors, or the C values, are used to adjust the resilient modulus at the in-place moisture to a lab, or adjust the back-calculated resilient modulus at the in-place water content to a laboratory equivalent resilient modulus by applying these correction factors. So as an example, this graph in the slide provides an example to illustrate the importance of input compatibility between the volumetric properties and the back-calculated resilient modulus values entered into the Pavement ME design software. So if we start at a back-calculated layer modulus of around, I guess, about 18,000 psi, that's our back-calculated layer modulus. And if we're using the default values, or the NDT in-place values that are about 62.2% degree of saturation, then as compared to almost 94% saturation. So if we start at a modulus value about 18,000 and we enter the in-place water content of about 94% degree of saturation, then the Pavement ME software and or the EICM will increase that value because the material will be drying out to a much higher value over time unless there's an increase in degree of saturation throughout the life of the pavement. Conversely, if we start with the default values, with one that's about 24,000 psi, and we're using the default value of water content, which is about 62% degree of saturation, then the program may not increase it as much over time. So the existing conditions become very important in defining which resilient modulus values are going to be used in the calculation of rutting, fatigue damage, and other critical pavement response values. Another example regarding the use of the data, as an example, we can start with, let's say, a default volumetric values and in-place modulus values. So if we have our in-place modulus value of about, let's say 7,500, but we're using the volumetric values, the in-place modulus values back calculated, but the default volumetric properties, then the program is going to decrease that value much lower as the degree of saturation increases. If, however, we use the in-place volumetric values of about 93% with the same resilient modulus, back calculated modulus, then the program is not going to decrease the values because the water contents are already relatively high. And so they're, in a sense, about 7,000 psi. If we use the default values for an A6 soil Our standard laboratory-derived resilient modulus is a little bit above about 11,500 or so. And then but that's at about an 82% degree of saturation. The Pavement ME program or the EICM is then going to increase the water content of that layer. And so as the degree of saturation increases, the resilient modulus is going to decrease. And as shown from the default values, both for modulus as well as water content and density, we get about the same value as using the in-place values with the back calculated resilient modulus, or the in-place values derived at the time of deflection testing, so they're about the same. However, if we would have used using the back calculated values, but the default volumetric properties, then the resilient modulus used in the response calculations, the resilient modulus of the subgrade soil for an A6 is going to be a lot less than what the in-place values are. And so this has to do with misinterpretation of inputs. And again, we want to make sure, as we've noted in other modules, that we have input compatibility. In other words, if we're back calculating a modulus based on in-place deflection test, then we should be using the water content and dry density that were measured at the time of deflection testing. And that will prevent misinterpretation of inputs and ensure we have input compatibility. So now let's move to rehabilitation design input level 2. For input level 2 for rehabilitation design, the results from the condition survey are used to define the in-place or the fatigue damage of the existing asphalt pavement and or layers. So we're measuring the amount of bottom-up fatigue cracking and the length of transverse cracking and defining it by severity level. The amount of cracking determines the in-place damage. The cracking severity, or the crack severity level, defines the load transfer efficiency default values that were estimated through global calibration. So the length and or area of cracks define the in-place damage. The severity of the cracks define the load transfer efficiency. So for rehab input level 2, the pavement distresses are important because that determines the in-place damage of the existing pavement layers and the inputs to the reflection cracking model, as well as defining the damage index of the existing asphalt layers for predicting future bottom-up fatigue cracks in the existing asphalt layers. So if we have 35% total lane area of bottom-up fatigue cracks, then that relates through to a damage index through our calibration relationship of bottom-up fatigue cracks as a function of the damage index. And so the amount of cracking measured at the surface then defines the damage index. Again, severity does not impact the existing fatigue damage. It only impacts the default load transfer efficiency used in reflection crack predictions. This just shows that the bottom-up fatigue cracks are impacted slightly by the thickness, the total thickness of the asphalt layer. A 4-inch basically would have more damage than the 8-inch 8-inch thick total asphalt layer for these two examples for the same amount of fatigue cracking measured at the surface, all other factors being equal. Rehab input level 2 is based on a subjective condition ratings. It's generally encouraged or suggested that input level 3 not be used other than for planning purposes and doing like preliminary designs of the rehabilitation strategy of flexible pavements. It's a very crude way to rate the condition, which is subjective, of the existing asphalt or flexible pavement. The condition rating in the manual of practice, which is defined in the manual of practice, then relates to a percentage of bottom-up fatigue cracks as well as a determined length of transverse cracking for the condition rating going from excellent, good, fair, poor to very poor. So the rehabilitation, in summary, the rehabilitation design input levels are based on, or there are 3 rehab design input levels. The first one is using back calculation of elastic layer moduli to define the damage in the existing asphalt pavement. The second, input level 2, uses the results from the condition surveys to define damage of the existing asphalt pavement. And then the third is simply using subjective ratings to determine damage of the existing asphalt pavement. So if we use specifically input levels 1 to back calculate, but we also have measured bottom-up or alligator fatigue cracks at the asphalt surface, and we use both of those on the same project, will we get the same answer for the same existing pavement regardless of input level used? And if they're different, why are they different? And which is more accurate? So some examples are included in the following slides in which we can get differences and what may cause those differences. We do not specifically address which is more accurate in the following slides. The statement or suggestion is to collect as much information that you can, non-destructive deflection testing, visual distress surveys, and use that in the rehabilitation design. And if we see that there is a big difference between the two, we need to stop and define why there is a difference. So this just shows the type of fatigue cracks. You can see in both, one is sealed, or a longitudinal crack in the fatigue cracks is sealed, but basically they have about on the surface the same type of crack severity level and basically about the same amount of area of fatigue cracking. So if we did a distress survey or did input level 2 and assume everything is equal for these two projects, then the amount of fatigue cracks or damage index predicted for the existing asphalt layer should be the same, and would be the same based on the distress surveys of total bottom-up, alligator, or fatigue type cracks. However, the core taken from the project on the left shows that the cracks are confined to the top 1 inch of the core. And this has taken many cores along the project, and the depth of the core varied from about a 1/2 inch, or really a 1/4 of an inch, to about 1 inch at the deepest. However, the one on the right shows that there's a lot more deterioration. The cracks go from the surface to the bottom. The bottom of the asphalt pavement is deteriorated, or intact cores could not be taken. So from a rehabilitation standpoint, if we just relied on visual distress surveys, our rehabilitation strategy selected for both of these projects would be the same. However, taking the cores as well as doing non-destructive deflection testing, the rehabilitation strategies for these two projects would be totally different. This pavement surface modification with basically a non-structural overlay would probably be okay or be appropriate with not much traffic. The one on the right, it would not be because it has a weakening. The back calculated layer moduli were significantly lower than the undamaged modulus, indicating a lot of damage in the existing asphalt pavement as compared to the condition on the right, in which the back calculated dynamic modulus were found to be greater than the laboratory measured or undamaged modulus curve or master curve. And that accounts for the aging of the asphalt. So it can make a difference. This also shows crack severity and magnitude can be similar, but the fix can be very different. These are two different projects. This shows a lot of deterioration at the surface, but the cracking goes from the surface all the way to the bottom of the crack. This is another core from another project which has segregation, longitudinal segregation at the surface, which caused top-down cracking, but the top-down cracking goes about to a maximum of about 3 inches. Generally varies from about 1 inch to about 3 inches below the surface, but it's caused by longitudinal segregation at the surface of the asphalt pavement. While this area has cracking throughout the entire depth, both top-down as well as bottom-up fatigue cracks, but also exhibits very severe crack deterioration at the surface. So in other cores, as this course from longitudinal segregation is removed due to raveling and it being dislodged due to traffic, this crack would be rated as very severe. So from a surface evaluation standpoint, both of these would be rated as severe cracks, and to reflect any cracks from the visual distress survey would reflect through an asphalt overlay in a very short time period. But the rehabilitation design strategy should be different and not the same. This design strategy would be more severe to include cold in place recycling. It's probably too thick for full depth reclamation, but cold in place recycling with thicker overlays and maybe some kind of reflection crack mitigation technique. This project could be still maybe cold mix recycling at the surface, may even include hot in place recycling to remove the segregated material and then put in some kind of treatment for reflection crack mitigation for those cracks that go below the wearing surface. But the rehabilitation strategy for this project would be a lot less severe, thinner overlay, asphalt overlay than for the project on the left. Debonded layers near the surface cannot be detected without the use of cores. Surface modification without structural overlays could be an option considered for both of these projects based on magnitude of cracking, which is low, and the severity of cracks, which is also low, of the surface cracks. basically no surface cracks here. Very minor top-down cracking at the surface here. So deflection testing and back calculation, as well as the use of cores, more appropriately as the use of cores, would or could indicate some structural deficiency rewarding debonding between the layers and result in a different rehab option, including a deeper mill and replace with a thicker overlay. So basically, if we were basing the design strategy or rehabilitation design strategy only on the surface condition without cores, we may not be able to note the debonding or shear cracks and or debonding between the layers below the surface of both of these projects, whether they included cracks going from the top to the bottom or not. So the rehabilitation strategy of just doing a surface modification would be totally inadequate for both of these projects. Another example is moisture damage or stripping may not always be visible at the surface or even from cores. However, deflection test and back calculation of layer moduli can detect reduced asphalt dynamic modulus as a result of damage and or stripping below the surface. So these dark areas for this core is moisture damage in which the back calculated layer modulus is a lot lower than the intact material, which does not distinguish moisture damage in the underlying layers. This, again, the darker areas as well as the bottom of the core shows moisture damage, and then mixture disintegration and or stripping in the lower layers. This also exhibits moisture damage, and without the use of the FWD or visually looking at the cores, we may not detect that the lower layers have an issue with moisture damage or stripping, and our rehabilitation strategy may be inappropriate. And obviously these two sections are examples of cores that do not exhibit stripping or moisture damage in the lower layer in these cores versus those that do exhibit severe moisture damage and stripping in the lower layers, which are not visible from the surface. So our rehab options between the two will be and should be significantly different. So in summary, there can be significant differences between just using rehab input levels 1 versus rehab input level 2. The suggestion is that both should be considered, especially for higher volume roadways. And the two together provide a more accurate representation and or selection of an appropriate rehabilitation strategy. So in summary, we have discussed the assessment of flexible pavements as related to rehabilitation as terms of Part A, and we also discussed the models and transfer functions specific to flexible pavement rehabilitation and the different rehabilitation design input levels for flexible pavements under Part C. We will now move to the section Part D of Module 9 that follow to explain and discuss the different options for rehabilitating flexible pavement. So this concludes Part C of Module 9.